example of the step response for a series RLC circuit. First thing we want to do is find those initial values. So let's look at our circuit for t equal to 0 minus. So notice we've used our step response notation here. So 100 u of t. So that's going to be 0 for t less than 0. And for u of minus t, that's going to be 4 for t less than 0. So this is 0, meaning it's shorted out, and we have just that one there. So what do we have? Let's draw it. We have 4 amps. Inductor looks like a short. Capacitor looks like an open. This is 0, so it's shorted. Whoop. That's not 6, that's a 4. I was doing 4 plus 2 in my head, jumping ahead there. 4, 2. V is here, and our current is through our inductor, where always, so even if we didn't draw it up there. Okay, so here's our circuit. What's our initial current? I of 0 minus, whoop, big hole. Current can't go through a big hole, 0. What about our initial voltage? So voltage between this node and this node. We have 2 resistors in series, 6, and we know the current going through them, right? So quick little mini circuit here. I have 4. I have 6. We have current going that way. So V is equal to minus 4 times 6. B equal IR, or minus 24 volts. So there's those initial conditions. So let's look at our circuit for time greater than 0. So t greater than 0. T greater than 0, this u of minus t is going to be 0. So this current is 0. That means it's an open or a hole. We can just ignore it, leave it off. It's just an open. For time greater than 0, remember what we're doing here, time greater than 0, this becomes 1, so now we have a 100-volt source. So just after 0, we have this circuit here for 100 to 1 Henry current voltage. And I know that the current through an inductor cannot change abruptly, so that current remains 0. I know the voltage across the capacitor cannot change abruptly, so that voltage is still minus 24. I need my alpha and my omega naught, so I know if I'm critically damped, overdamped, or underdamped. Alpha equals R over 2L for a series circuit. What's my R? Well, if I deactivate this, I have those 2 in series. So I have 4 plus 2 over 2 times my L. So I have 6 over 2, I have 3. Omega naught for all circuits is 1 over square root of LC. That's 1 over the square root of 1 times 0.04, or that gives me 5. So I have, I don't have my page pulled up here. I have omega naught greater than alpha, which means I'm underdamped. If I'm underdamped, I know that what my generic solution looks like, and I also know that I need omega D. Did I calculate that on here? Somewhere, I believe, omega D is equal to the square root of omega naught squared minus alpha squared, or 4. So my generic solution, we're looking for the voltage, so we'll just find that. My V of t is going to be v of infinity plus e to the minus alpha t minus 3t times a1 cosine omega dt plus a2 sine omega dt. So we need to find a few things still, right? We need our final value. We'll go ahead and find that. Switch back to blue since we're over here. So I need, my final value is t much, much greater than 0. So when t is much, much greater than 0, my inductor looks like a short, capacitor looks like an open, la-da-da. We've done this so many times now. I think you get the drill, I hope. (100 volts). Just have these nodes in parallel with those nodes. And we have a few initial conditions already, right? We found these to start with. We don't have any dVs yet, but we have those. So let's use them. So v of 0 equals v infinity 100 plus e to the 0, so 1. Cosine of 0 gives us 1. Sine of 0 gives us 0. So all we have is this term when we're plugging in 0. We have e to the 0 times a1 times 1 plus a2 times 0. And that's equal to minus 24. So I end up with just my a1 as my unknown in here. And a1 equals minus 124. So there's my first one. Okay, for my second one, I need to take the derivative, right? I need v dv of t by dt. So we take the derivative of this. Obviously a big pain in the butt, but that's okay, we got to do it. So I don't know if I need to do that on here. I think I'm going to skip that on the video because it will take several minutes to do, and it's just a derivative. First times derivative of the second, plus second times derivative of the first. If you can't do that, go back and look at your calculus book, please. It's critical that you can do that. And what we get will be minus 3 times a cosine 4t, sorry, a1, plus b sine 4t e to the minus 3t plus 4 minus a sine 4t plus b cosine 4t e to the minus 3t. There we go. But we still need that initial condition, right? Well, we know the current through a capacitor is C dV dt. Well, I know the current through the capacitor because of my initial condition here, right? Everything's in series, it carries the same current. That current was 0. So that's equal to 0 because this initial condition is 0. So I have this. That means that my dV dt is 0. So this whole thing up here is equal to 0. So dV of 0 by dt equals 0. Plug 0 in for t. You get minus 3a. I'm sorry, I switched from a2 to b. That's a little confusing. So these b's should be a2s. There we go. We got that fixed. So minus 3a1 plus 4a2. We know a1 already is 124. Plug that in here, and you get a2 is minus 93. So now you plug your a1, your a2, your v infinity all back into here. And we get our final answer, which looks nasty. Bolts. So there you go. We'll work one more example problem in the next video.